All right, here we go. Last but not least, we have the fourth conic section, the hyperbola. And we have studied hyperbolas before when we studied rational functions. We saw a hyperbola when we graphed the equation y equals 1 over x. So this is a variation of that comes from the conic sections, and the interpretation of it is more general. So we're going to look at the general formula for the equation of a hyperbola. By definition, a hyperbola is the set of all points xy in a plane, the difference of whose distance from two distinct fixed points is a positive constant. So it sounds almost like the definition of an ellipse, except it says the difference of the distances from two fixed points. So remember, with a circle, we had the set of all points equidistant from a given singular point. For an ellipse, we had the set of all points equidistant, the sum of whose distances was equidistant from two given points called the foci. And then remember the parabola, we had a foci and a directrix, and it was a set of all points equidistant from the directrix and the focus. And so now we're going to have two foci, and we're going to have the set of all points whose difference between the 2 points is going to be a set distance. And so we're going to have something that looks like this. So those are our four conic sections, and they're all defined in terms of slicing a cone and also in terms of a distance away from either 1 point, 2 points, or a point and a line. Okay, so circle, let me finish writing these down. Ellipse, this one's called the parabola. You guys are very familiar with that one. And this one is the hyperbola. All right, so remember how the ellipse could be either vertical or horizontal. Same thing with the parabola. It could either open left or right, or it could open up or down. And then the hyperbola can either open left, right, again, or up and down. So if you look on your cheat sheet, which I hope you've all printed off by now, the cheat sheet gives you the formulas for all of these. And the circle comes first, and it's the shortest, and then the parabola, and then it goes back to the ellipse, and then the hyperbola. And these three have quite complicated equations. So you're going to be able to use that cheat sheet to help you with the formulas, but really I want you to have an understanding of how these equations work in general. Okay, so let's take a look at what the standard equation looks like. Again, it's a variation of the distance formula. So you're going to see that x minus x squared. So it's x minus h. That's going to be the center of your hyperbola. And it's going to be over a squared. So far it's looking just like the ellipse, but it's going to have subtraction in the middle. And then y minus k squared over b squared equals 1. So honestly, the only difference you see between the equation of the hyperbola, which we're doing today, and the equation of the ellipse is going to be that subtraction sign right there. If it was an ellipse, it would be plus. But it's a hyperbola, so it's going to be subtraction in between there. Now, the variation that I wrote down first has a horizontal axis. That means it's going to open left and right, and it's going to have an axis that goes right through the foci and the center, if you want to call it that. And so we call that a horizontal transverse axis. And then we can have another variation of that that's going to look exactly the same, except it's going to have the y squared part before the subtraction. So it's going to look like this. Still going to equal 1. Still going to have a squared and b squared, but this time the axis is going to be vertical, and you're going to have it situated where it opens up and down. It has foci here, and you can call that the center right there. All right, so there's standard form for the equations of a hyperbola. HK is called the center, but again, the center is not part of the set of points that satisfy this equation. A is the distance from the center to the vertex. So we've got these vertexes. A is the distance to, that's supposed to be 2, A is the distance from the center to the vertex. And so these are two vertices here and here. I've labeled them with a V. This is C, and then these are the foci. B is the distance from the center to the end of the conjugate axis. Now, I haven't used that term yet. Conjugate axis means the other axis, and I'll show you about that in just a minute. C is the distance from the center to the foci, and C is not in the equation. So remember when we did an ellipse, we had to have a little kind of quadratic formula looking equation to find C. We're going to have the same thing here, but it actually looks exactly like the quadratic formula. A squared plus B squared equals C squared. So you're going to need to find C to be able to find out how far it is to the foci. And then like an ellipse, there's a measure of eccentricity. And eccentricity is a measure of how flat the branches are. And so you can use ECC. E kind of means something different to me, so I put ECC. It's C over A. Okay, now, there's also these asymptotes. The way I drew my hyperbola, they don't look very much like hyperbola, to be honest, because there should be these asymptotes that the hyperbola zooms towards, but never actually cross. And the asymptotes are slanted lines. They're not horizontal or vertical, they're slanted lines. And so the equations of the asymptotes, those are tricky to find. But the equations of the asymptotes are the following. The equations of the asymptotes, asymptotes. The equations of the asymptotes, it'll be on your cheat sheet. Y equals K plus or minus B over A times X minus H. And that's if you're horizontal, okay? Or Y equals K plus or minus A over B times X minus H if you have a vertical. So this is for if it opens up and down, and this is for if it opens left and right, like that. Okay, so we're going to go through examples. This is going to take us a while, but there's the equations. Let's start off with an example that's pretty basic. Let's start off with this one right here. First example. 4x squared minus y squared equals 16. Fix that. Okay, the subtraction sign is the giveaway that this is a hyperbola, not an ellipse. We see both x squared and y squared. We see that there's different numbers in front of the x squared than there is in front of the y squared, so it's not a circle. And the subtraction sign is what tells me that this has got to be a hyperbola. So it's supposed to be equal to 1. So it's almost in proper form to be equal to 1. If I just divided through by 16, I could put this into standard form. So the 4/16 reduces to x squared over 4. The y squared over 16 just stays y squared over 16, and then it equals 1. Okay, I definitely started with an easy one for a reason, because it takes us a while to figure this out. So the center of this one is 0, 0. Because there's nothing added or subtracted to the x's and y's, no other x and y terms, this is a center of 0, 0. And a is the number underneath x, because x comes first before the subtraction. So a is going to be the square root of the square root of 4, which is 2, and b is going to be the square root of 16, which is 4. Now, why are we going to need this? Well, those two numbers are going to help us define c, and c is going to be the distance to the foci. So we're going to go c squared equals a squared, which is 4, plus b squared, which is 16, so we get 20. We've done 20 a bunch of times, haven't we? It's 2 square root of 5. So the value of c is 2 square root of 5. Okay, so we've got the center of this circle, and I'm going to draw it. Let me change this to graph paper so that we can take a look at what this looks like on a graph, okay? So I'm going to draw this so that you can actually see what develops here, because I think it's pretty obvious once you see it on graph paper. Okay, center 0, 0. All right, A is the distance to the vertices. So if we start at 0, 0 and we go 2 units to the left and 2 units to the right, we get negative 2, 0 and positive 2, 0 as being the vertices of our hyperbola. So vertex, center, vertex. All right, now the two branches of the hyperbola are going to curve around the foci. So that's the next thing I want to find. I want to find the foci. So these are the vertices. We've got those. All right, now what about the foci? The foci, according to our directions, are going to be the center plus and minus C. We don't need B directly yet, but we need C. So 2 square root of 5 is about 4.5. So I'm going to go to 2 square root of 5, 0, going to the right, and then to the left, negative 2 square root of 5, 0. This is easy one because it starts at 0. So I'm going to go about 4.5 out. That's going to be my focus. About 4.5 out the other direction. That's going to be my second focus. Okay, now I'm just going to sketch what we see developing here. This is going to be a hyperbola that's going to head outward. It's going to curve around its focus, but there's going to be some asymptotes that are going to contain the branches of this focus and keep them in check. So how do we draw the asymptotes? Well, I gave you a formula for the equation of the asymptotes, but there's kind of a cool way to figure it out without actually looking at the equation, and I really like to draw them this way. So let me delete those green marks that I made there so that we can actually get this exact hyperbola in place. So what you want to do, it doesn't like my erasing. I'll do it by hand. Okay. All right, so what you're going to do is from the center, you're going to go out to the vertices, that's A, and you're going to draw a vertical line through the 2 vertices. And then from the center, you're going to go up B, so we're going to use B as well, and you're going to draw a horizontal line through B. From the center up B and down B. So B, negative B, A, and negative A. And we're going to create this box. And that box is going to be the area where the hyperbola is not. And if we draw the diagonals through that box from corner to corner, we're actually going to draw the asymptotes. So I'm going to try to do this very exactly, but you know how it is when I try to draw. So I'm drawing these as dotted lines because these are the asymptotes. They're not actually part of the function, but they're boundary lines that keep the function from passing them. So putting those in helps me to be able to now use the vertex and draw exactly where the branch of that hyperbola is going to be. I know exactly how wide it's going to be because it's going to start at the vertex and it's going to hug those asymptotes as it heads out to the left and to the right. And again, I shouldn't draw it like that. I don't know why I did that. It's supposed to hug the asymptote and get closer and closer and closer to the asymptote, but never actually cross it. So let me fix that. There we go. Okay, so there we have it. There is our hyperbola. Now, you can find the equation for the asymptotes if you would like to give the equation of the asymptotes. Again, it goes through 0, 0, so it's y equals mx plus b. And we know that in this case, it crosses at 0, 0. So its y-intercept is 0 for both of the green dotted lines. But let's see, this is going to go up 4 and over 2. So it has a slope of 2. So 2x, and then y equals negative 2x. But the equation that I gave you, let's go back up here just a little bit, is a over b. Remember, a was 2. Oops, I'm on the wrong one. b over a, 4 over 2. I'm using this one right here. 4 over 2 times x minus h, which is just x minus 0, plus k, which was also 0. So that one was pretty easy. Again, if you just look at the box, it's pretty easy to figure out the slope. You're going to use a and b for the slope. And then you have to adjust if it's not centered, if it's not going through the origin like this one was, it's not centered at 0, 0. You're going to have to adjust that y-intercept. Okay, let's do another example where it's not quite as easy. And it's not in standard form. That one was easy to put in standard form. We just had to divide by 1. Well, let's take a look at a little bit harder example. Let's look at this one. 4x squared minus 3y squared plus 8x plus 16 equals 0. Okay, how do I know that this is a hyperbola? That's the first question to ask. We know that it's a hyperbola because of the subtraction and both x and y being squared. So let's try to arrange it a little bit and see what it looks like if we try to put it in standard form. So I'm going to put the x squared terms together, the x terms together, I'm sorry. And then I'm going to put the y squared second because it's subtracted. If the x was being subtracted, I would have rearranged those in the other order. And then I'm going to take the 16 and I'm going to move it over to the other side. And we'll see what kind of constant we get, and then we'll divide it out to get equals 1. Okay, so remember when we completed the square when there was a number in front, the first thing we did was we factored out that coefficient. And then we did our completing the square. So we said half of 2 is 1, squared is 1. That creates x plus 1 squared. That's the perfect square that we wanted to get it in standard form. We'll leave the 4 out in front. Now, remember, when you add 1 inside of parentheses that has a number out in front that's been factored out, you actually added 4 times 1. So the number that needs to go in the plus blank over on the other side is 4. So we have minus 3y squared. I don't need to do completing the square on that one. If you want it to look like standard form, here's what I would suggest. I would write it as 3 times y minus 0 squared. Okay, there you can see it nicely then. And then that would equal 12, right? Because negative 16 and positive 4 makes, negative 12. I forgot the negative. Okay. So now we need to divide by negative 12 on both sides because in standard form it's supposed to be equal to 1. Okay, we accomplished that, but we kind of messed things up over on the left because now we have 3 and 12, well, negative 3 and negative 12 reducing to positive 4. So I'm going to have to switch the order of this. I'm going to put the y minus 0 squared first over positive 4, and then the second fraction is going to be minus x plus 1 squared over 3. The reason we need to do that is because we need it to be in standard form, which means that whichever variable is squared needs to come second. So we switch the order by dividing by negative, it rearranged the order. So this is actually going to be a hyperbola that opens up and down. So let's see what we're looking at here. Here's my axis, or here's my x and y axes. And my center is going to be at, now be careful when you do the center here, because the center is the x coordinate first. So even though it comes second, it's going to be the opposite of 1, what's in the x parentheses here, and then paired with 0. So it's going to be negative 1 comma 0. So here's the center this time. All right, the distance to the vertices. Now in this case, the vertices are on a vertical axis, is going to be a. So a is the square root of what's underneath the y, so 2. So from there, I'm going to go up 2 and down 2. So my vertices are going to be at negative 1 comma 2 and negative 1 comma negative 2. Okay, so I've got the center, I've got the vertices. All right, the foci. To find the foci, I need to do c squared equals a squared plus b squared. So c squared equals 7. So c is the square root of 7, which is like 2 point something. So from the center, I'm going to go up 2 and a little bit. These are very close together. Focus, no, vertice, focus. Okay. All right, and now I need to make the boxes so that I can draw the asymptotes. So I've got the foci. Let me put their coordinates down. The coordinates of the foci are negative 1 comma, what is it? The square root of 7 and negative 1 comma negative square root of 7. There we go. There are the two foci. Okay, now the asymptotes. The equations of the asymptotes are going to be the equations of the lines drawn by the following box. I need to go up 2 and down 2. I already did that. And then the square root of 3. Square root of 3 is like 1.7. So I'm going to go out 1.7 and 1.7 from the center. I'm going to draw this box. Not through the foci. There we go. And now I'm going to draw my asymptotes. They're going to come right through the center and through the corners of the boxes. I just like to visualize it. Okay, here we go. It starts at the vertices and it hugs the asymptotes. And because the y squared came first, this is a vertical hyperbola with a vertical axis. Okay, I do need to give the equations of the asymptotes. So the equations of the asymptotes are going to be y equals, let me go back up here to the equation, y equals k plus or minus a over b times x minus h. Okay, k is 0 plus or minus, I already forgot, a over b or b over a? For this one it says a over b. So a is 2 over b, which is the square root of 3, times x minus h. So minus -1 is going to be plus 1. Does that seem right? The positive slope of 2 square root of 3, and it goes through, yeah, that looks about right. Okay, so there's the equations of the asymptotes straight from the formula, just using a and b. All right, I think that's it for that one. Okay, sometimes you'll have to complete the square on both. I'm sure you guys could do that. I guess I'll do one more example. I know it makes this video really long, but I'm going to do one more example. Okay, so here we go. We have 9x squared plus 4, ooh, not plus, minus, it would be an ellipse if it was plus, minus 4y squared plus 18x minus 24y minus 27 equals 36. Okay, I'm going to go 9x squared plus 18x minus 4y squared minus 24y. I'm going to move the 27 over to the other side. I've already got a 36 there. I suppose I could have added those two together. And we'll deal with it in just a minute. Okay, so we've got them grouped. Now let's do some factoring because we're trying to get this into standard form. So we need a perfect square here. So let's pull out the 9. And let's figure out what number we would need to put in that blank to make it a perfect square. So we would need half of 2, which is 1, squared, which is 1. And so we have the perfect square, x plus 1 squared. Now remember, we added 9 times 1. So over on the other side of the equation, let's see, that's 63 if I add those two together right there. And then I just need to do a plus 9 to compensate for what I did there. Okay, second factoring group. We've got a -4 that we need to factor out. That's going to leave me with y squared plus 6y plus blank. Half of 6 is 3, squared is 9. We just created the perfect square, y plus 3 squared. But remember, we actually have -4 times 9, so that's -36. So we need to add a -36 on the other side to compensate for that. So altogether, 6, let's see, that's 72, and -36 would be 36 again. Okay, we're getting close. We need to divide by 36 on both sides. When we do that, we get that equals 1 that we were seeking for, and it's not so bad, is it? Because 9 and 36 gives a nice integer value of 4. And then when we reduce the second group, we get 4 and 36 reducing to 9. So at least they came out nice numbers for a squared and b squared there. All right, so a is 2, b is 9, and c, remember, is a squared plus b squared. So the square root of 4 plus 9. So we're going to get the square root of 13 for c. Those numbers we're going to need for the asymptotes and the foci. All right, so here we go. I'm not going to draw it this time because I want to show you can do it without drawing it. But this is a hyperbola that opens left and right. Okay. Its center is at HK. So look inside the parentheses. With the x's, you're going to get your h. With the y, you're going to get your k. So the center is at -1, -3. The vertices, you're going to take -1 and add a. So -1 plus 2 is going to be +1, -3. And then -1 minus 2 is going to be -3, -3. So there's the two vertices. The foci are going to be the center plus c. So -1 plus the square root of 13, -3. And -1 minus the square root of 13, -3. I know it looks weird like that, but at least then I've got it exact. I don't have to write the decimal. And then the last thing I need to do, I forgot about the eccentricity on the last two examples I did. The eccentricity is just c over a, so the square root of 13 over 2. That's a measure of how flat this hyperbola is. And then the last thing I need is the equation of the asymptotes. If you don't even want to think about it, you're just going to do y equals, and you're going to take the x coordinate, which is -3, the y coordinate, k, plus or minus, and then you're going to go b over a, so 3 over 2, times x minus k, which is -1. So there you have it. And you can leave it in that form. I mean, some people might actually multiply it out, get rid of the parentheses, and give it in y equals mx plus b form. But you're welcome to leave it like this since we're dealing with conics. And we know where these numbers came from, the h, the k, the a, and the b. All right, so these are the equations of the asymptotes. All right, so that finishes our lesson on hyperbolas. You're going to want to definitely make sure that you do the homework. And then on Monday, we're going to be having a study guide. But you're going to do the study guide as an assignment, and then you're going to do a quiz. It's kind of like a simplified version of all the stuff that we've been doing, but it's thinking backwards. So I'll give you some practice on that on Monday. All right, good luck.